Hello, welcome to an episode of Beam There, Done That. I'm one of your hosts, Alan Wyman. Today we have...
Hi, I'm Francesco Cesarini. Been active with the Erlang ecosystem for the last 30 years, seeing a programming language evolve into an ecosystem of languages.
And then we have Brooke Zelenka.
Yes, hi. I'm Brooke Zelenka. I'm a senior researcher at Ink and Switch, working on local first CRDTs and distributed system stuff in general.
And international celebrity, Robert Virding.
Yes, I'm Robert. If you've seen the movie, yes, I'm Robert. And now I'm working for Erlang Solutions.
Hello, Robert.
Sigh. If you're not careful, I'll show you the movie instead, right?
Well, we do have the ability to show that, so I don't know if we want to get into that today. For those who don't know what's going on, there was a famous movie you can look up for yourself called, was it the Erlang movie? I believe that's what it's been titled. I'm not sure.
Erlang the movie. Yes,
it sounds more epic.
And then there's also a very politically incorrect sequel, which we won't go into. But because that's not what we're going to talk about today. What we're going to talk about today is kind of the evolution of distributed systems to modern local first architectures. And these are the architectures which, one end of the spectrum will work with devices offline, but on the other end will also allow users to be in full control of their data.
Erlang was designed for systems that you deploy once and run for forever, while the local first is designed for systems that don't need to have a constant connection. Both share the same DNA, dealing with the reality of an unreliable world. Since we have Robert over here who co-invented Erlang, I think it's really great to hear from him about this. Maybe Robert, you can talk a little bit more about when you start off working on Erlang and your conclusions and how you came up with Erlang itself.
We were out to solve a problem. That was the basic idea for the language we had, working for the computer science lab at Ericsson. And one of the things we're looking at is how we can improve programming their telecom systems. And we had checked up a number of existing languages and systems. This is mid-late 80s. We found that none of them were really suitable for what we thought how the problem should be attacked. So we started looking at doing our own language. And that is what became Erlang in the end. We had ideas about what was necessary to solve the problem. We didn't know that much about it. So Joe Armstrong and myself, we came from outside Ericsson. Didn't know much about making telecoms, except making a telephone call. Mike Williams had worked much longer in Ericsson. And we were fortunate to work together with another group inside Ericsson who were looking at doing a prototype of a new system for it. And they were very experienced about the application. So we could discuss the problem, our ideas for solving the problem with them, and they would come back with critique and comments about how what we had done and how they felt if this was a good or bad solution or not. So we could arrive at something which ended up being a very good way of solving the problems they had in a way they felt was a good way of doing it. That's what we were doing.
Brilliant. Thanks, Robert. And Brooke, why don't you tell us a little bit about what you're working with today?
Yeah, absolutely. These days I'm working on a model called Local First, which it's not just my team and company doing it. It's a whole model. It has its own conference, has all of these things, where instead of there being a single place for data to live, each replica of the data is considered to be just as good as any other. And this means that you don't have to wait for things like getting a response back from a server or where are you going to host it? Are you going to self-host it? All these questions. Your browser is just as good as the server somewhere. I currently lead a team adding security to this because, as you can imagine, if you don't have an auth server, you don't have access to an auth server, and things will still work, if it's on any replica, even, in your browser. How do you secure access to your data? Do you use encryption? Do you use fancy things that are based on process models? How exactly does that work? And so, I'm working on basically making data secure and work everywhere, including offline.
This is why I'm super excited about today's episode, because with Robert and Brooke, we have the perfect bridge between the foundational architecture approach Erlang and telecom networks gave us in the 80s, alongside the whole movement of sovereign data, which we're seeing today. Thank you for being on the show. I'll start with a question for both of you. If we treat a user smartphone as a long-running Erlang process, how does how does that shift the responsibility towards data ownership and state management?
Do you want to? Who wants to go?
The question of, if from a process-oriented model, right? If we think of this as a long-running process, that can be helpful, having this idea of where the data resides. But fundamentally, I think it's a question of what sort of consistency you have or that you want. So if you need there to be exactly one view of the data and there to be a single source of truth, then running things on a phone can be very challenging, right? If you go through a tunnel, nobody can access your phone. Maybe people can't use your phone as a server. They can't dial into it directly. And this is where the kind of techniques that I work on become very helpful. So instead of having to build an application and then immediately decide, how am I going to deploy this? How do I get other people to use it? I need to have a long-running process somewhere out in the world to access that data. Taking a data-oriented view, which is a very sort of functional programming view of things, where the data itself is the thing that fundamentally matters, and using things like, people especially if you've worked with Phoenix, you may have seen CRDTs kicking around. These are data structures that can automatically merge together. Think like Git, but without the Git conflicts. Then it doesn't matter where the data lives. Now it's liberated from any particular place. And yes, you need to be able to talk to other devices and other processes to get their view of the data. But just like how you can have Git branches and Git forks and have them merge back together later, this lets you not have to worry about there being one true place where the data lives. And having it now run on your phone means that you don't have to worry about, are you going to self-host a server? Are you going to use, a hosted service? How exactly are you going to do this? It can just run wherever the data happens to be. So that might happen to be on your phone. That depends on you not having to making this trade-off, right? That there isn't one view of the data. Kind of, again, making all of your application work a little bit like Git. That's not going to work for everything. Right? If you want to ingest all of the data off of, say, Blue Sky, you're not going to keep that on your phone. So there's this question of what is the problem you're trying to solve, and what does your application actually try to do? And having a process-oriented model, Erlang processes, being the canonical example here, let you move between these two seamlessly, because they're going to move data around for you. They're not giving you references into some shared memory like you would have in, say, C++. Everything is just getting moved around as pure data. So we're still in this functional model. And so we can move seamlessly between these two worlds of my data can run everywhere without an internet connection, or if it's connected, then I get extra capabilities. Or if I need to centralize some data on a particular server, that's also going to work because maybe it's very high throughput workload or something like this. It's again, using Blue Sky Firehose as an example, which is why, I did Erlang and Elixir for many, many years, and why I keep coming back to those things to see, okay, if we take just CRDTs on their own, they're actually really good for a lot of things, but they're not good for everything, right? So how do we use these new techniques in a way that don't limit us from being able to do things that are at much higher scale? We should be able to scale both up and down.
We were always with the processors for different reasons of making sure that they owned their own data, and no other process could access that data. So you had complete control over where the data was. That was just, we had other reasons for doing it, but that was just one of those facts that allow you to build systems where you have complete control over where the data is if you need to do that. And that's what we were after. We had, as I said, other reasons for doing it, but the same properties we were after. That's about it.
What I'm hearing here is in Erlang, you've got a process, and that's isolated. It's an isolated island with its own memory, just like local first user devices, that same isolated island. And I think the core lesson here is what we've been saying all along is that shared memory is evil. It's a bug, not a feature.
I can just say, yes, most definitely. Shared memory just gives you lots of problems, right? Getting rid of it solves a lot of problems.
What I think is really interesting is, the story of how you came to these ideas of processes and these other kind of things. And, how did you test these theories and come up with these theories and make sure that they were sound? Because you don't just say, let me just try this, let me just wing it and start building this thing, right? You must have said, okay, somebody did something similar, or I have this idea, let me just try it on a small scale. Seems like there's something there, and then go forward. Can you give a little bit of feedback about that? Because I don't think I've ever heard anybody talk about, that process of how you have the ideas and then finally have the whole beam and everything else from there.
Well, we started thinking about the problem, and we realized from the very beginning that if you need a large switch, there's a lot of things going on in parallel. So you need something to be able to handle things concurrently from the very basis. And we had ideas about doing this. And as I mentioned, we were very fortunate to have this group of people, who were working on a new prototype. They were looking at a prototype, who were very knowledgeable about the system, so they could give us very good feedback about our ideas. So if we have concurrency, what does the concurrency mean? What does it have to solve? If we're communicating with things, what's a good way of doing that? Getting one another. The problem was, of course, the system as a whole must not crash. So when things go wrong, because things always do go wrong, how are we going to handle errors in such a way that it was suitable for building the system? And we came up with ideas for this, and we got feedback of whether these were good ideas or bad ideas. Did they work? Were they suitable to use in the way we were thinking that they should be used? Right? It's all very well saying, yes, you've got concurrency, but how are you going to use this in a nice way? Fault tolerance, yes, but how are you going to do this? Do you let things crash? What happens when you let things crash? What happens if you don't want to let things crash? How can we handle this? And again, we were thinking about these things. We got a lot of feedback for it, and the system evolved as our ideas evolved, and we got feedback from the users if they were good or bad ideas. Because to be honest, some of the things we came up with just weren't very good. We could work this out in such a way that it worked, that did things. And it took time, but in the whole, we came up with what became the Erlang language. What I found very interesting was later finding it was suitable for doing other things than telecoms, which we hadn't been planning from the very beginning. Right? It just suited for doing web servers. And then when you start thinking about the problems, that they is doing something completely different, but the requirements were very similar. What you wanted concurrency, you wanted fault tolerance. You couldn't accept that your web server crashed, because that would mean that people would not be very interested in coming back and things like this for it. And how you do this, and it just worked. And as what Brooke was talking about, it's worked for many other things as well too, beyond this, which are completely different type of problems what we were thinking. But they just have similar requirements. I think I can just say one thing that meant that Erlang could do this was one of the requirements, one of the principles we had is we would not supply solutions to the telecoms problem, but provide tools, the right tools, so they can make the right solution they wanted to, which means it could be used for other solutions as well, which had the same requirements. So in that sense, we didn't solve telecoms, but we gave a set of good toolbox for building that type of application and other types of applications as well. Just some ideas, some thoughts about it.
I mean, to link, Robert, what you're saying with what Brooke was saying, when you have the let it crash approach, when you have CRDTs and eventually consistent models, what you do is, well, and correct me if I'm wrong here, but what you tend to do is you move a lot of that complexity where you need to handle eventually consistent data and models, when you need to handle recovery strategies to the business logic of the code. And could you tell us a little bit about that and a little bit about the trade-offs you need to make when taking those design decisions?
Having CRDTs means that, similar to an Erlang process, you have isolation between processes or between, or devices, however you want to, break this up, wherever the data lives. And it's a different kind of fault tolerance than what you're getting in an Erlang process. Things will continue to work offline because you're not needing to communicate, but it doesn't have anything like, restarting processes or all the nice supervision stuff that we normally get out of OTP. Having to think about, okay, I've merged in some data. Actually, maybe I'll take one step back briefly just to make sure that the audiences can follow for the people that aren't familiar. So CRDT is very fundamental to this style and has this weaker consistency, right? So I've said before, we don't have in one particular place. It can be distributed around. And so a very simple version of this is if you have a list I can say I need to buy apples and eggs and cheese, and then maybe I need to cross off that list and say, I actually don't need cheese. But just like how in Git, you keep all of the history, I also have to keep all of those removals for all time, and I can't actually get rid of them. Some of the things that we need to deal with are different users seeing different versions of the same data. So if they've received the same updates, they'll see the same stuff. But you now have to think about this at the UI level. How do I expose to the user, hey, we're out of sync with somebody else who's also looking at this document, but we also get some extra, functionality of that. I can go back in time and look at previous versions of the document, sort of for free, in giant scare quotes, by having all of this data still kept around forever. But that also does mean that unlike having one place, every device has to keep a copy of all of these things. So the different kinds of tolerance that we're getting are, as long as we've persisted the data to disk, the next time that we come back up, we'll be in that previous state. We can tolerate network partitions, so being offline or having a disrupted network. But it does come with some of these other considerations of well, how do you show that to the user? We're not really thinking about crash recovery. So if your logic is bad and you've put your document into a bad state, that doesn't manage your, the constraints on your system. How do you recover? Well, that's kind of outside of the system now, right? So these are all, you don't get anything for free, right? In any of these systems, everything comes with trade-offs. And so it always comes down to a question of which things should be inside your model versus not, and how much do you want to show the user different things versus not. So if you have a Google Doc and you get on an airplane, you can read it, but you can't edit it. That's one set of trade-offs, because you can read a copy, but you can't update it because the update happens on a server somewhere. Versus with the CRDT, you can still update it locally, but you might be out of sync with the person sitting next to you on the plane because you synced at different times. All of these things come with trade-offs, and which is why I don't think there's any one silver bullet to different kinds of resiliency in these systems. It really depends on the kind of thing that you're trying to do, and how crash recovery versus, say, partition tolerance are kind of on different axes.
Almost sounds like, if you think of the whole kind of lineage from phone switches, to CRDTs, telecom switches had to handle concurrent calls and asynchronous signals, without a global lock. And this is pretty much, what CRDTs do for, document editing as the example you used, or data syncing today. So you don't realize it, but there's a much, much tighter connection than what we think. Now, question for Brooke, and then we'll throw it over to you, Robert, as well, because I'm sure you and I have discussed about it as well, but discussed ideas in this space as well. But how do Erlang's constructs like Gen servers and its message passing semantics provide a mental framework for implementing modern CRDTs, and also capability based security for that matter?
This is one more thing concept to give people. If we're in this world where data can live anywhere and we don't have an auth server that everything is being routed through, which, both on one hand, if you're doing things at very, very high scale, a single server isn't going to scale for you for auth. But then also, if you want to bring things down onto a device and have that offline capability, how do you prevent someone from editing this document? They have a copy locally. Right, and especially something that seems to really get people thinking in the right direction recently is if you have LLMs that are creating an agent that's spawning all these different sub agents and doing all of this processing on data, and you don't know exactly how they're going to behave. Well, we can't register them to some central place and central authority. We need to have process isolation for them, and so there's this model called capability security. That is really just barely an extension to the Erlang process isolation model. Essentially, each thing that you want to grant access to, you create a little proxy object, and you give a handle to, let's just say, an LLM agent, for example. And your agent only gets access to certain, maybe to one file, or to one row in a database, or wherever. And if your agent and its sub-agents, because it can pass that PID around, starts to go off the rails, you can turn that proxy off. And it can't access all of that stuff anymore. You don't have to do, if this is an external system, You don't have to do sandboxing and firewalls and all this other kind of isolation. We're getting that for free from having process isolation and from doing this message routing. And the actor model is, maybe to flip it around, the capabilities model, object capabilities as they're sometimes called, are a pattern of use of actors. And as long as you have that process isolation, you can get very fine-grained access control without having to maintain a database with business logic, with all of these, Byzantine rules in it that are, they grow over time for every possible edge case. Instead, you pass around PIDs, and that is your access control. And so it becomes very, very natural. The way that we already use actors in Erlang is a kind of capability-based security. So for things like CRDTs and gating access to them and saying who's allowed to sync with who, well, we don't have a central place, a central list, and that list could always be out of date, right? Because it's causally consistent, it has the speaker consistency. So doing this process-based model solves a lot of problems for this. We can then also take this and make it static as well. This is a whole other discussion, but having that very flexible, very, very sort of organic model fits very, very nicely into the Beam. And so I was chatting with Robert earlier, and he was saying, well, obviously, that's what we do anyway. I'm like, yes, but it has a name, and it has patterns, and we can use this to guard things that turn out to be very, very difficult problems, right? How do you do safe AI? It's really difficult because you can't trust them. So how do you deal with mutually distrusting agents? Turns out that there's a whole subfield for this that uses exactly these things, isolated processes, routing of messages through. Sometimes in that literature, they'll call those call trees supervisors, even though that's different from crash recovery. So it can be sometimes a little bit confusing. This ends up solving a lot of problems, and it just falls naturally out of having actors.
Robert, one question for you. Have you ever thought of distributing state in Gen servers, abstracting away from where Gen servers are executing, and then let the state, if you've got multiple copies of the data, come in sync again using CRDTs?
Not really. I mean, again, for what Brooke said, we have provided a relatively versatile tool which allows you to put things together in the way you want, right? And we had no idea it would be used like this, to be honest. Spreading data out and distributing data, you have to decide yourself how you want to do and what you want to do with it, and then do it, right? The system does not do it yourself. If you want to distribute data, you have to build your system in such a way it will do that, and then you can decide how you want to control where the data goes and where the data does not go. So I can set up a set of servers that are talking with each other, and they can agree to, yes, they'll spread the data between them, and it's up to them, and they will they will have control over the data, where it is, and who can access it, because they're the only ones who have access to it. And if someone comes along and asks for data and they say, no, I don't trust you, I'm not going to let you do it, they'll just say no. And they can do that, right? Because they have the complete control for it. And how you want to build your system to do that, that's up to you, because you know how you want to control this, right? We couldn't guess that. We couldn't do that for it. We could provide some tools that help you do it, but we could not decide what you wanted to do. And again, through OTP, we provided a set of servers and things for doing stuff, but there is no limit to, you have to use them if you need something else. So if you want to put them together in a way we didn't see, you can do that for it. Yes, we provided Gen servers in OTP, and they're quite general things. They can be used for most cases, but if you need something else, then you write your own server. We provide supervisors for supervising in a different way from what Brooke was mentioning. We're talking about what happens when processes crash. Do we need to restart them or not? But you can do other things in a similar way, in different ways for doing that as well too, keeping control of stuff. And again, as Brooke mentioned, if you're going through accessing data through a process and you kill that process, then the data cannot be accessed from that way. And that's just how it works. It's not a feature we thought of as such, planned for it, but it's just how it was done, right? So when you communicate with a process, you say, I want to talk to this process because you've decided that's the process you want to talk to. I send requests to it. And if the process is not there, well, that just doesn't happen. If the process gets the message and says, no, I don't want to reply, it doesn't reply. That's it. It's very much up to how you build and put the system together. What I see is where the problem comes, deciding what you want to do, right, and where to do it. Right?
Yeah, and to just yes and something that Robert was talking about, there's some really interesting work from a few years ago. Chris Micklejohn has two projects. One's called LASP, LASP, which is this CRDTs as distributed data inside of a, automatically for all of your variables system, and then also partisan, which is essentially an extension of both, like a process model and CRDTs into sort of a more cohesive system that's a little bit more OTP-like. Both very, very interesting systems. And people have been taking these and kind of running with them. So there's a research group doing, I believe the top level paper is New Directions in Cloud Computing, which is Hellerstein's group. Really interesting stuff to explore in that direction. It's just not really widely used yet, but both for scaling reasons and for, in sort of, in a cloud context, as well as some of these questions about fault tolerance and user agency and things like this. It ends up being a really interesting thread to pull on. Really gets you thinking about how the different constraints from both the tools that we had in the toolbox and the constraints that we had on the sort of problems that we're solving, again, to Robert's point a moment ago, drive the design for things, right? So if you think about in the 80s or 90s, you have the internet, but the tool that you have is that there's a beige box under your desk. That's how you're going to access the internet. You need to rent somebody's server somewhere if you want to host your email. This leads to those companies scaling up and having their one copy of this data in one place. And when AWS US East 2 goes down, we all get a snow day. This really gets baked into the system sort of from the ground up. And we always try to extend that model as far as we can. And that is absolutely the right solution for a lot of problems. It's not the solution for all problems, right? So, do I think that we need to have data centers for every application on the planet? Absolutely not. They're very useful for other things, totally, right? And so even say Erlang, coming from a telecoms perspective, gives us certain tools, but we can repurpose them and reuse them in new ways that don't require putting everything through US East 2.
I can just make one comment. It's been used for many things that we never realized existed, right? And I think the one thing we did right here was making it a set of tools. It's a toolbox with a set of tools in you can use for many different ways. But you have to decide what you want to do with it. And I can also just say, as another comment here, Erlang can't solve all problems. It can't be used for everything. We know this was never a problem for us, because we realized from the very beginning there were some things Erlang is not good at. Then you need to use some other language, and you can plug that in and do that. And there are ways of doing that. And we did this from the very beginning, right? We didn't solve the whole problem. So we don't see that as a problem. It's a set of tools. They're good for some things, but not for everything.
I just wanted to ask a question about the whole idea that you're out there to solve this one particular problem, and solving this one particular problem has somehow managed to solve many other people's problems. There's many things I want to ask about this. One is that how does that make you feel, knowing that you've solved a lot of issues, especially with the day and age of, this is a long time ago, X or Twitter going down, this kind of problem where you can't get to it. And then the other thing too is, what personally for you has been the most interesting problem that you seem to have solved that you never thought you would?
Most interesting problem, there are lots of them. I was talking to Brooke earlier today, and she described a lot of problems I never thought about, right? Which are very interesting. There's a lot of other things to look at as well too. I think we were very lucky in some way to arrive at something which was very close to the actor model, because that is a very nice system. And I can just say, we did not know about the actor model when we were designing this. We went towards something which we felt would best solve the type of problem we were looking at. And we read later that people said that Erlang was implementing the actor model. And we said, oh, are we? And we went on about this. And I met Carl Hewitt later, and I mentioned to him I was a bit embarrassed because we didn't know about the actor model when we were doing this. But he saw it as a very positive feature because of the actor model, because they'd arrived at it from a more theoretical point of view, and we'd come from a very practical point of view and arrived at basically the same solution, which showed the power of the actor model. So that was something that's very positive as a feedback from the whole system for it. And again, another positive feedback is it's being used for so many different things we never realized. Even starting off with such relatively simple things like web servers and things like that for it. Again, when you look at them, they have very much the similar type of problems that telecom systems had, but in a different way, right? You want reliability, you want massive concurrency. You don't want the system to crash because that gives a very bad feel for the people using it. But they're doing completely different things. And as I mentioned before, we realized from very early on that we weren't providing a language or a system that could solve every problem. It could solve a bunch of problems, and if there are things that they can't help you with, then you would write them in other languages and do that. That's something we do not see as a strange or as any negative feature of the system as a whole. Again, it's a toolbox, and I think that was very good. And what I like is just seeing how it's being used for other things.
If something's worth inventing, and it's useful, it's good that it's been invented at least twice, if not more. And then CSP was also very, very similar. Just to add to what you're saying, Robert, what do you know now that you wish you knew when you started working on Erlang?
I don't know, really, to be honest. The requirements might have been different. Computers are much bigger, much more powerful than they were then. Maybe we could have found other solutions in existence today that could have been used as part of it, or in such a way we didn't have to attack that problem. I don't know. It works. That's basically all I can say, really. It works. I can't really give a good answer to that, to be honest, because and I'm not saying that there aren't a lot of things that were developed after Erlang which aren't very good. There are a lot of things, but how they would have affected our work, I don't know. Maybe if there's another system had come along, we wouldn't have had to do our work at all because there wouldn't have been a need for it. Someone else would come up with another solution to the problem, and we wouldn't have to do it. What we would have done then, I don't know. Where we would have arrived at then, I don't know. And what that solution would look like, unless it looked like Erlang, I have no idea. Again, it's very difficult to see. As I said, we had our problem. We enjoyed working with it. We saw doing something that worked and something that was helpful and useful. That was also very, very satisfying. We had long discussions about what the system should look like, and got, as I mentioned, a lot of feedback saying which of our ideas were good and which were bad. We didn't come up with only good ideas or good ways of how they could be used. So I don't know. I can't really give an answer to that question, I'm afraid.
Brooke, I have a question for you. When it comes to this idea of having these massive data centers, it seems to be that we're still on that part. But looking back at Erlang, I mean, you have node to node to node. You can have this whole kind of process, and everything's all distributed. Do you feel that we've gone into a bad direction with that, or do you feel that we should start looking back to the way things are local first and CRDTs and sort of like that?
Great question. So I think that we ended up in a place in the industry where we had a hammer and everything thus looked like a nail. There are many different ways of structuring, sort of if we want to get all technical about it, your network topology, putting things into single, data centers that companies scaled really quickly through the 2010s, but has also, it has other trade-offs. Needing to decide, if your typical development workflow is you've got something running on your laptop, maybe you have you've built the application end to end, it's working, and then immediately it's a question of where do I run this? Because I'm going to close my laptop and it's going to stop running. There's nothing special about CRDTs as a solution to this problem. There's many different ways of tackling it. It's just we decided that really massive hyperscaler data centers were the way to manage this, and that our application architecture should look just like having a single process on a single machine for the entire application. And both what Local First teaches us and what Erlang teaches us is that we can distribute that. We can break applications up There's this old line about if you have a single node, you don't have fault tolerance, right? You have to distribute it ideally geographically, right? You get that for free out of local first. You also can set things up that way in Erlang. You want to have replication. You don't want your application to go down. Handing over your entire application to a single platform has, whoever, AWS, Firebase, whoever, exposes you to a lot of platform risk on one side. And then also for users, they don't get to make many decisions about their own data, right? That's starting to change. There's starting to be, legislation and things like this to give people the ability, an option for exit. Projects like Mastodon and Blue Sky that are trying to help solve some of these problems. But as application developers ourselves, I think it behooves us to start thinking a little bit more about the distribution of our applications, right? Not just saying, okay, I'm going to release this to the one true server. Where should that live? Should you have replication? Should you have, right? And not just making it the single default all the time. How do we make it convenient for people to deploy apps in ways that are more fault tolerant in this sense, where if there's a power outage, half the internet goes down. Why? Right? If a company decides to, you have all your data with a startup and that startup folds, how do you get your data out? Is it in an interoperable format, right? So it starts to open up all of these other questions that we haven't asked since really the cloud started in the early 2000s.
I almost get the feeling that, well, it's not a feeling, it's what's happened is that we've gone in and we replaced distributed systems, which are hard, with centralized systems, which are easy but fragile. This movement of local first, which we're seeing, is a return to the original kind of more distributed vision, I think, that Erlang was originally built for. Looking at distribution, looking at a kind of peer-to-peer local first world. In it, you can't really rely on a login button, for a central server to step in and actually protect the data. A question for you, Brooke. I mean, in a system, with a central authority, how do we use Erlang's isolation principles to ensure that the data remains secure, even when it's living on a stranger's device or on a local edge node?
There's two angles on this problem, and I'll handle them separately. First is, how do you gate access to the data in the first place and the ability to update it, let's say. And the other is, once it's actually over somewhere, how do you protect it in place, right? Like literally it's already gone somewhere. How do you prevent misuse of that data, or to the degree that you can? The first one is more, I think, easy to think about from an Erlang context. This is the thing I was talking about before, where if you have process isolation and some mechanism of authentication, so you need to know who you're talking to, or the ability to hand out PIDs to them, or references. They can be a near reference or a far reference, doesn't matter. Then you can control, without having to put into some central database rules that say Alice yes, Bob no, between these hours, all of these things. And you can set up routing that just uses these processes directly. And that's very easy there is no verification. Do you have the PID or not, right? And it's impractical for them to guess, especially PIDs on another machine, right? Over the internet, especially. You don't have to encode all of these things and then make your business logic for auth checking this massive set. You can do that just purely using message passing. And that's it. On the other side, how do I know once I've actually sent messages around and data has leaked, let's say, right? Like it's out there now. How do I prevent people from pushing updates to everybody else who has, say, a CRDT, right? Any two replicas of this can stitch together automatically. How do if I have a reference to it and I know the identity of something, I can break that reference, but I might not have prevented every link in the entire system, right? I have a connection to, some sync server, but also to some, friendly peer that also has a path. We do, for this, defense in depth. So we use end-to-end encryption. So if you use Signal, basically all of your application data can live in something like Signal. It stays encrypted everywhere it goes. You know who's allowed to update it because you have these references, so you can have both a PID or something that's signed, and you prevent access to future updates by using, without getting into it in too depth here, fancy cryptography that rotates keys over time. So just like how in Signal, if someone is kicked out of a group, They can't read future messages. Same thing for your application data. The insight here is that you have to both guard who's allowed to access the data, who's allowed to ask for it over the network, and also protect it in place. So sometimes called defense in depth. Cryptography works in place, but it is not sufficient, because if somebody leaks the keys and they can still access the data, it's not enough. So you need this process isolation or at least reference isolation to prevent people from downloading even the encrypted data.
Kind of consolidate what you're saying, if I understand it correctly, is we need to move towards a kind of capability-based security where the message itself and having knowledge over the process identifiers contains a permission to act, kind of echoing, and I think, Robert, I'd love you to comment here, echoing how Erlang processes communicate, but also how modern kind of decentralized protocols operate today. Is that right?
Yeah, so there's two layers. There's exactly the Erlang process, passing PIDs around side. But if you're doing CRDTs and you want those to be secured, there's an extra layer on the data itself. So we have pure data, it's immutable, and that access control also has to have an immutable layer layered on top. Capabilities in and of themselves, or sometimes called process capabilities, or in this case, object capabilities, let you protect access to processes, and then you need additionally to protect the data in place too.
Robert, I don't know how much you were involved with amnesia, but I know when I first heard about the CAP theorem, I had a kind of aha moment. That explains a lot of the things about the behavior of amnesia. I don't know if you've had any experience there and how you reacted when you first heard about the CAP theorem.
Not much. I have played with amnesia, of course, or amnesia, depending how you want to call it. It was an interesting solution to problems that we have about managing data over distributed systems. In this case, just pure Erlang distributed systems, yes. And how you wanted to save data, update it, things like this for it, and which level of reliance you want it on. So if I update something, do I want to know for certain it's been updated everywhere or not, right? Or maybe if I don't need that, maybe I can just say, write it out. It'll eventually get there, hopefully. Things like this for it. So but no, I was not part of the group or developing amnesia. I can just say one thing. Getting back to what it was before, it just uses the standard parts of the standard tools we did in a different way, right? And I think that's, as said before, part of the strength of Erlang. It can be used in many different ways for a lot of very different, interesting problems, right? Which I don't have solutions to at all. But we managed to do something useful. And again, it can't be used for everything. I mean, Brooke mentioned cryptography. We don't have cryptography in this system. If you want to have cryptography, you have to add something which does it. Right? Fine, do that. Same with other things. If you need serious numerical calculations, then you add something which does that. Fine, it's good. You can just include what you need for your problem to put it in, and Erlang won't solve all the problems. It'll help you use these different solutions, put them together perhaps, but it won't solve all your problems. That was something we knew from the very beginning, and we didn't attack that. I think that's about the best I can say, I think.
Now, Robert, I wanted to ask you a question. Now, in the late 80s, you were solving the problems of millions of connections, phone calls to, a single, need to be connected without a single point of failure. If you could send a message, going back, punning on Erlang, if you could send a message to Brooke and other kinds of local first developers and tell them, one single immutable truth, what would you want them to know?
You mean send back to them? Right, okay. I would say, well, an obvious truth is you have a difficult problem. It's definitely not a trivial problem to solve. We can help you part of the way, but the rest you'll need to do yourself and understand what's going on, and also very well understand what we can't help you with. So you can get around that. I think that's about the best I can say in this sense, that the problem will grow over time as the possibilities for doing it and what the system will allow grows. Because we now can have a lot of different data centers interacting with each other, you get these set of problems you didn't have before, right? Before we had one computer standing in there, or maybe a couple of computers standing in one place working, and that was where all the data was much easier, because you had much more physical control over who could access it. You just pulled out the wire and they couldn't. That simplicity's gone now, because the problem's evolved. And it will get both better and worse. Better because you can do more things, and worse because you'll have other things you need to attack to solve these problems, and what you want the system to do and how to do it. Do what you can and try and do the same thing as we managed to do, was to get an understanding of what the problem we're trying to solve was. Work out what actually you need to solve. Right? Do you need to worry about this, or need to worry about that, or not? Right? What is your thing? That's not easy to do. To be honest, you need to interact with other people, other groups who are maybe potential users in some way, and find out what they require, what they think is important, which from your point of view might have been totally uninteresting. But they think it's a central feature that they need to be attacked. And that's about all I can say, I'm afraid, I think, with this.
Love the question, Alan. I will take it and rephrase it for Brooke. So, Brooke, today you are solving the problem of millions of users wanting to own their data without a single point of control. So, if you could send a single message back in time to Mike, Joe, and Robert, what would it be?
That's a hard one, because it was such a different set of constraints, like Robert just said. Other than thank you, because we do think through these things in terms of processes, and I often reach for, my colleagues will sometimes laugh because I'm often reaching for, the way we do this in my case in Elixir is I think they managed to really, whether or not they were aware of the actor model at the time, really nail a model in a way that you don't always get, even if you're working from a single use case, right? And having a thing to test against. Sometimes you overfit against that. And I wonder if it's because of the background in things like physics, et cetera, that they came from, and not only being stuck in programming language brain the entire time, found a really interesting model that was not in wide use elsewhere, right? They found a part of the design space that was really helpful. I don't know if I could really send anything back for that use case. I'd maybe send back some of the stuff from the Erlang that was doing some extensions to actor model stuff for capabilities. Overall, mostly it's been a really useful model for me to think through all of these problems. I think it ended up working out pretty well in the end. So
I think we're all grateful they did not give up their day jobs for a career in acting, I think.
No, that was probably very good. But if you watch the movie, watch the second one as well too. That's really worth watching.
I would have thought one of your regrets would have been maybe hire a script writer for that video, just to make it a little bit more, a little bit more interesting. And but the way it is, I think also has its kind of charm to it. So I'm very happy that you did that, and that video still holds true today. It's really a great example of why this is a really good system to have for what it's out there to solve: the fault tolerance, the message passing, and even clear debugging. Like that's something that people don't even talk about. Oh, my language does this, does that. But from the get-go, it seems like Erlang really had a great way to debug what happened, which is something that we really need, and it's just an afterthought for a lot of people in a lot of languages.
Yeah, I can just say that there's a lot of support. There was then, but there's even more now, support for tracing and debugging the system while it's running. So you can keep track of what's actually going on, and check if it's what you hope it's going on. You can do that and look that. You do have the dynamic code upgrading while the system is running, which is not used very much, but it's there. It is not always easy to use, to be honest, because you might run into a lot of problems doing it. Unexpected problems. But there's support for keeping track of what the system is doing, and that I think is very important. And as I said, it's being improved all the time while the internals of the system is being developed. There are a lot of things you don't notice in the language itself, but in the implementation have improved over the years and keep improving as well, which I think is very nice.
We often say that Erlang was made for the internet age, even though it predates it. We say it was built for multi-core architectures, even though it predates them as well. And today we've actually seen that the future of independent data looks a lot like a history of telephony switches. So by moving away from a single database in the cloud and returning the state to isolated processes and devices, we aren't just developing solutions that work offline. We're actually building a more resilient user-owned internet. And so we can actually joke that Erlang, whilst it predates local first architectures, was built for them as well. What do you think, Robert?
Yes, just very thankful for what people feel about it and how it's done and how it's being used now for it. I just very appreciative for that. Again, just accepting the fact that it is much more versatile than we thought and we originally planned for. I can just say I was very surprised that someone would want to use Erlang for doing web servers. I thought, who would else want to do Erlang with doing web servers? But then you think a bit about, and a lot of the problems they have doing a big web server was similar to what we were doing looking at telephone switches. You want massive concurrency, you want fault tolerances and all these type of things. So in that sense, the problem is much more general. And for, again, parts of the problem of what Brooke is describing, Erlang suits very well. Now, of course, other parts of her problem have to be done completely else. Rethink, because they're very different. There's nothing strange about that. And that's, again, for other things Erlang is being used for. The parts of it, you just have to rethink and add new things to it, or implement in different languages or other things, and just do it right and get it and do it. That's just my sort of opinion about the whole thing and thoughts about it.
This episode was recorded on the 21st of March, 2026. And I think for the first time, we're at least the three of us are all in the same room in Vancouver. And I think I'll go in and actually take a selfie of us so that you actually believe it. Post this on social media, even though the backgrounds look very different. But there is Brooke and there is Robert. So we've got the luxury of it. And well, Alan, you'll have to join us next time. Thank you, everyone. Take care. Bye-bye.